Hello everyone. Today let's solve the problem little elephant and inversions. So you can read the entire question. I'll just summarize the question so that it is easy to understand. So what the question says, the little elephant has array of integers. So the little elephant contains array of integers. It might be 1, 2, 3. I'm just considering the example. Array of integers. So here and wants to count the number of pairs, and he wants to count the number of pairs. Let's consider this one within L and R, such that the combined sequence from the start of the array to L, then from and then from R to the end has no more than k inversions. So starting from L and then from R, it shouldn't be more than k inversions, right? So the sum should not be more than k inversions. That's what they have given. An inversion, what is an inversion? Basically, the inversion is a pair of indices ij. It can be any index here. It can be this one, 1, 0, index starts from 0, right? 0, 1, 2. It can be this index. It can be this index, any index. So an inversion is defined as a pair of index where I less than j. If this is I and if this is j, then I should be less than j. Then first, mostly it has to be sorted, right? So this has to be less than j. That's what we have to keep in mind. So I less than j, and the element I is greater than the element at j. So index mean the element at I is greater than the element at j. So sorry, the element I at I has to be greater than the element at j, means the value at I should be greater than the value at j. That's what they have mentioned here. And what is our main task? Our main task is to find the total valid pairs, nothing but L, R. Total valid pairs L, R based on the given constraint. So based on the given constraints, we have to find the total valid pairs. This one, right? So total valid pairs, this one we have to find. So this is the question. Let me delete this one. Let's consider the approach and let's go with the implementation, right? So just give me a second. As usual, first we will be starting with the input reading or input handling. So the first step, we'll go step by step. First step is always input reading or input handling. This belongs to basically input. So basically we'll be making use of the JavaScript or the Node. So first step is always input reading. By this time you'll be knowing the input reading or the input handling part, right? So let's move to the main part or the core logic. So first what we will do, we will compress the coordinates. Since the elements of the array can be very large, so elements of the array can be of any length, right? So since the element of the array can be very large, up to it can be up to 10 to the power of 9. So we need to map these values to the smaller range to efficiently manage the counts in our data structure. First thing is the elements in the array can be of any order. So any this thing, yeah, array can be very large, basically can be up to 10 to the power of 9, right? So we have to map these values to the small range to efficiently manage the counts in our data structure. So this we can call this one as coordinate compression, right? So we are compressing the coordinates. Since the values can be very large, we are just compressing the coordinates. So after this one, we map the values to the smaller range to efficiently manage our counts in our data structure. We will be going with the this one. A main approach that we'll be going with for this problem is binary index tree, or we'll be going with the Fenwick tree. So here we'll be using two BITs, or we'll be making use of the two binary index trees to maintain the counts of indices. So we have to maintain the count of the indices, right? To maintain the counts of the indices, we'll be using two binary index trees in the compressed array, which allows for the efficient range, sum queries and updates. So just remember that we'll be making use of the BIT here, two binary index tree, or the two Fenwick trees or Fenwick trees. Why we are making use of two binary index trees over here? So we have to count the number of indices in the compressed array, right? For that reason, we'll be making use of the binary index tree or the Fenwick tree. So after making use of this one, the next step is we will be going with the 2-pointer technique. So nothing but we will iterate through the array with 2 pointers. So we'll be iterating through the array with the 2-pointer approach. So just give me a second. We'll be iterating through the array with 2 pointers to find the valid pairs. So we have to find the valid pairs over here within the compressed array, right? By making use of 2 BITs. And then we will be iterating through the array and we'll be finding the valid pairs. The first pointer, I will iterate over the potential values of L, this one. The first pointer will iterate over the valid, this thing, potential values of L, while the second pointer, J, will find the rightmost position where the number of inversion remains. This will make sure that the number of inversions remain within the K. So what will I do? So I will iterate over the potential values of L, and the second pointer will make sure that the number of inversions will remain within the K. So this will be the fourth step. So we'll be going with the 2-pointer approach for the iteration. So just remember this one. First one is this one, coordinate compression. After this one, we'll be going with the binary index tree or the Fenwick trees. Why? We'll make use of the 2 BITs just to maintain the counts of the indices in the compressed array. So this is one thing. This you have to remember. And also for the iteration, we'll be making use of the 2-pointer approach. Fourth step. After this one, what we will do? The fifth step. Let's come to fifth step. So in the fifth step, we will be finally we will be counting the valid pairs. So for each valid I, we will add to our total count based on the number of valid J values that meet the condition. So based on the number of valid J values that meet the condition, we will add our total count. We'll add our total count for each valid I. So that's what we will be doing here. We will be counting valid pairs. So this one, fifth one, third, fourth, and fifth. So this will be implementing in the code, right? You'll just get to know very clearly when we write the code. So this will be the approach. Next, we have to output the result. So we have to display the result, right? Finally, we'll get the result in the fifth step. We'll get the result in the fifth step, but we have to output the result. So for displaying, as we are going with the Node.js or the JavaScript, I'll be just making use of console log and we will be displaying the result, right? Nothing but the output. So this is the approach that we will be going with for this particular problem. So let's start writing the code so that you'll get to know in a good way or in a better way. So first, let's import the necessary modules that is required. So I'll just give here const fs equals required of fs, right? This is one thing. Next, we have to read the input. So for this one, I'll just give input equals fs dot read file sync of. Let's start from 0, and this will be, we'll set the encoding to UTF-8. So after this, let's remove all the unnecessary spaces. To remove all the unnecessary white spaces, I'll be making use of trim, and also to read the input line by line. So I'll just go with the split. So let me make use of the regular expression. Here I'll just give /n/r. So after this, I'll just go with plus this. So this is fine. Next step, let's write the function that is nothing but we'll be writing the custom function to read the list of numbers. We have to read the list of numbers for the input, right? So we'll be making use of the numbers here. So we have to read the list of numbers. For that, I'll be making use of the custom function read num. I'll just give here read num. We can read in this way. By this time, you have to know the input handling actually. So I'll just give here count plus plus. So within the same line, if we are having the distinct numbers, then we have to leave the space between them. For that purpose, I'll just make use of the split and leave space over here. So next, let me make use of the map, and let me take some random character name. I'll just take a here. Let me consider %. We'll convert this one to integer a, 10 I'll give. So this is fine. Next step is we'll write the function to read the single integer. We have to write the function also to read the single integer, right? So it is similar to this one itself, readnum itself. Where again, we'll be making use of the custom function. I'll just make use of readInt. Here I can write in this way. Percent of single number, right? We are converting this one to the number. Input of, so I'll just give count plus to move to the next line. And then here I'll just give 10. Next step is let's write the function to read the list of integers. So again, here this one will be the custom function read list. So this time it will be input of, let's increment the count here. Then if the numbers, distinct numbers lies in the same line, then we will be leaving the space, and finally we'll be mapping using map. So this will be %. So just give me a second. Why did I use the array? This has to be %, again a comma 10. So this is fine. So this is just the input handling. Next, what we will do, as I have said, we'll be making use of the 2 binary index tree, nothing but now we will write this one, BIT class definition, nothing but the binary indexed class definition. Let's go with this one, class. I'll just give the name BIT. So here within this one, constructor of n. So this will be this dot BIT. Here this will be new array of n plus 1. Also let's fill this one with 0. And also we have to store the size as well, right? So here we'll be going with n. So I can just write, I'll just point this one within the constructor. I'll just give, sorry, what am I doing here? Just give me a second. This dot n, I'll just give n. This is fine. Let's write the method to update the binary index tree, update the BIT. So I'll just take update over here. Here this contains 2 parameters, index and value. So let's increment the index. Also let me give while index less than or equal to size, nothing but this dot n here. So what we will do, we will update the BIT with the value. So I can just write in this way, right? I'll just give this dot BIT of index. This one I can write index plus value, nothing but same thing. Here I can just give value index. So finally we'll move to the next index. To move to the next index, I can just give index equals index plus idx and minus idx. In this way I can just write this one. So this is fine. So after we update we will update the BIT, then we will write the method to calculate the prefix sum. So to calculate the prefix sum, I'll write in this way. Let's make use of the prefix sum method itself. So within this, I'll just be taking the parameter like this. So here within this, I'll just give index. We will convert to 1 based index. And also let me do one thing. I'll just consider this one. Let answer equals, let's initialize ns2, or you can take result variable to 0. And while index is greater than 0, because index has to be greater than 0, right? So then only what we'll do, we will sum the values. When the index is greater than 0, then only we'll sum the values and move to the parent index. So I can write in this way. Answer equals answer variable I have considered, right? This dot, I can just consider this one, BIT of index. Also next idx equals idx minus same thing, idx and minus idx. So this works. So here we have to return, right? We have to return the prefix sum. So to return the prefix sum, we have initialize ans, variable ans, right? Just if we return this one, this is enough. Nothing but we are returning the prefix sum over here. So this is fine. Next step, after writing the method to calculate the prefix sum, let's write the method to get the range sum between the indices. So this is simple. I'll just give range sum. We have to calculate the range sum between the two indices, right? I'll just take L and R, these parameters, nothing but the two indices. So here I can return in this way. Return dot prefix sum we have to calculate, right? Prefix sum I can make use of here. Prefix sum of R minus this dot prefix sum of this will be L minus 1. So this is fine. Nothing but here we are calculating the range sum. So I hope this is clear. Next, let's start writing the core logic for this particular problem, right? Within the function solve. So just give me a second here. I'll just name this function solve here. So let's read n and k first. So I'll just make use of this one, destructuring operator. Let me make use of read num to read. So we have written the custom function read num, if you remember here. So I'll just come here, this line number 4. You can just remember here. I can just give read num. We are reading n and k. Then after reading n and k, we have to read the array a as well. So I'll just give here. We have made use of the read list, if you remember, along with the read num. So I'll just call read list here. Next, as we had discussed in the approach, if you remember, first step is we'll be going with the coordinate compression on array A, right? So we are going with the coordination. Going with the coordination compression. Why we are going with the coordinate compression here? Because the array will be huge, right? It can it can contain any number of elements. So for that purpose, first what we will do, we will sort the indices based on value, nothing but, and then we will map the original values to the compressed values. That's what we will be doing in simple steps. Nothing but coordinate compression on array A. So I can write in this way. Let B equals, this will be spread operator of array n dot, this will be keys. So this is fine. Let's sort this one. How can I write? I'll just write x comma y. This one, a of x, as we are making use of arrays. Within the arrays, we need to get this a of x minus a of y. So this is fine. I hope this is clear. We are just sorting indices based on the value. Next, let's initialize previous and current values to 0. So I'll just give prev to 0. Also, current value we are initializing this one to 0 as well. So this is fine. Next, as I have said, after this one will be mapping the original values to the compressed values. So initialization part is done. So what we'll do, we'll map the original values to the compressed values. Nothing but we'll go with the iteration. So I'll just come here. This will be individual index of B. So here B, this one. We have initialized this one array and we have sorted here, right? So we are considering the individual values of B, individual index of B. So is here previous value not equal to array of index, idx of A, A of idx. Then what we will do, we will increment the current index for the unique values, as well as we will update the previous value and assign the compressed value. So I'll just can write like this. First we will increment current index. Next we'll update the previous value. Updating the previous value is nothing but, again, a of idx. In this way we can write. Then we will assign the compressed value. Nothing but a of idx equals current. So this one I can write. Else what we will do, we will maintain the compressed value for the duplicates. So here I can write in this value a of idx equals current. So just we are maintaining the compressed value for the duplicate. So this is fine. Next step is, so let's create the two binary index trees. So as I've said in the during the approach, so we'll be creating the two binary index trees, right? So how can we do that? First thing is, I'll just take one variable named bit here. Let's consider new this one function bit of size n plus 1. Also one more bit, nothing but of size n plus 1 here. Size n plus 1. Next step is, we will initialize the inversion count. Nothing but I'll just give current value to 0. Then let's update the first binary index tree, first bit with the first element. So I can just write in this way, right? Bit of 0. So in the update, we have already written update. What we are doing, we are updating the first element, updating bit with the first element. It comes with the pairs, right? So I can just give a of 0, 1. So in this way, I can write. So next, let's initialize j to the initialize j to the end of the 0. Nothing but the value will be n. So I'll just give let j equals n. So I hope this is clear till here. Next, let's iterate from the end of the array. Our initialization part is done. Next, we will be iterating from the end of the array. So this will be reverse iteration if we are iterating from the end of the array, right? So I can write in this way, n minus 1 I greater than 0. Let's decrement the value of I. So after this, count inversions. So how can I write the count inversions? I can just take, I have already to count, I think. So I'll just take CNT. Here. Bit of 1. We're calculating the prefix sum of, let's make use of a of I. This one minus 1. Also plus a of 0. If a of 0 is greater than a of I, then let's go for, let's display 1, or we will be displaying the zeros. Nothing but this is count inversions. Next step is if current value plus count, if this is less than or equal to k inversions, then we will update the current inversion count. Nothing but I can just write in this way, right? Current equals current plus this one, count. After updating the current inversions count, we will update j to current position. So here this is easy. Then we will update the second bit as well. I can write in this way, bit of 1 dot, we'll be making use of update, nothing but of a of I, 1. So this is what we will be doing. Else, what we will do, we will stop if the inversion exceeds k. So inversion has to be less than or equal to k. If it is more than k, or if it exceeds k, then we will start the inversion. So I'll just make use of the break here. So we'll break out from here. So this is one thing. Just give me a second here. After this step, what we have to do, we have to calculate the result based on j. So this is simple. I'll just go with, if j equals 1, then let's return n into n minus 1. This one, or divided by 2. Nothing but if all the pairs are valid, we will be returning this one, n into n minus 1 by 2. So this is one thing. Next, what we will do, else, I'll just make use of else if j is equal to n, nothing but the last index or last value, sorry. Then no valid pairs are found, then we will directly return 0. We can directly return 0 in this case. So I hope this step is clear. What we have done here, we have calculated we have calculated the result based on the j. Next, let's initialize the answer. This is the final step basically. So I'll write this one first. Let's initialize the answer. to n minus j. So here, let's start the iteration. It will be let I equals 1, I less than n minus 1. Let's increment the I. So after this one, we have to update the current inversion. So current equals current plus I minus bit of 0 prefix sum of a of I plus, so here this one has to close here itself, k of I plus bit of 1 prefix sum of a of I minus 1. So this is one thing. We are updating the current inversions. Next step will be updating the first bit. How can we do that? I can just give here bit of 0 and update over here a of I comma 1. So this is fine. We are updating the first bit. After this step, if current value is greater than the inversions k and j is less than or equal to n, then we can adjust the current inversions, update the second bit as well, and move the j forward. Nothing but we are making use of the two-pointer approach here, right? So we are making use of two-point approach and carrying on with the operation. So first we have updated the first binary tree. As I have said, now we'll be updating the second binary tree. What is the condition? Current has to be greater than the k inversions and j has to be less than or equal to less than n. So then we will adjust current inversions as well as update the second binary tree, as well as we will be moving forward. So I'll just make use of the while loop because current has to be greater than k and also j has to be less than n here. So first let's adjust the current inversion. So I can just give here I plus 1 minus bit 0 dot, let me give prefix sum a of j. A of j here I have written, right? Same thing. Again, one more, this one, wait, index 1. Again, let's make use of the prefix sum. This will be previous element, right? So this is nothing but a of j minus 1. So this is, I hope this is clear. Next step is we will update the second binary tree as well as we'll move the j forward. So this is simple. We can just write b of it. We have to just update, right? So I'll just make use of the update. We have already written update. This will be a of j comma minus 1. This comes with pairs minus 1. I just give. So we have to move the j forward. So let's increment the j over here. So I hope this is clear. Next step is to, so if current value is greater than k, we will stop. If it's still, we will stop if it is exceeding k, right? So I can just make use of the break statement over here. So if current value greater than k, then I can just write break here. So after this step, this is done. We have completed all the steps, right? Next, we have to count the valid pairs. So if you remember, I have initialized the ANS variable over here. So this one here. ANS, so I can just answer variable, this one, I can just write n minus j to count the valid pairs. Finally, what we will do, we will return the answer. Nothing but we will return the total count of valid pairs. So to return the total count of valid pairs, we'll just go with return answer. So I hope this is clear. Finally, what we will do, we have got the answer now. We have returned the answer. So we have to print the result, right? So we can print the result of the solve function, entire solve function. So I have to give like this. So I'll just give console log. I'll just call the function here, solve. So we'll get that answer here. So this is it. Let's see whether this works or not. I'll just come here. let me copy this one. The output has to be 3. Let's check here. So here this is saying unexpected token, right? This has to be I equals n minus 1. So line number 59. Let me come to line number 59. First, let me change this one. So here, sorry, this has to be I equals n minus 1. Then required is not defined. So did I make any mistake here? Just give me a second. So here this is, I have made use of the required, right? So this has to be required, not required. Sorry, this is one thing. Let me run this one again. So here count is not defined. We have where line number 4. So input of count best place. So just give me a second over here. Let me come to line number 54. Here let bit, within the array I have given new bit. Here I have just considered new, right? This has to be bit. We are considering 2 binary index trees. So I forgot bit here. Let me hit the run again. So count is not defined, we are getting, right? So I have defined that one. Didn't I? Just give me a second here. Yeah, I have missed the initialization of the count here. So let me give count equals 0 over here. So let me hit the run again. So yeah, now we are getting the output 3. So let's check what output we need to get. So yeah, we need to get output 3. So this code works absolutely correct. So let me copy this input and let's check. We have to get the output 6, right? So yeah, we are getting the output 6. So this is working properly. Just give me a second. So I'll just come here. Let me click on submit code. So here the problem E, right? So I'll just come here. Let me paste the code over here and hit the submit button. Let's wait for some time. Let's see. It says in queue, right? Let's wait for some time. So this is taking long time, right? I hope the code works. So yeah. So let me reload the page again. So yeah, let's wait for some time. So you can clearly see here the code got accepted, right? So the code works absolutely correct, except I had done some typos here. So here I hadn't initialized this one, count to 0, that one. And instead of require, I had given required. That was one thing. And also in the line number 54. So I'll just come here in the line number 54, I think 55, this one here. Here we are considering 2 binary trees. Here I didn't mention bit. These were 3 mistakes that I had done. So now I had corrected this one, I have corrected this one, and this code works absolutely correct. So here you can clearly see this got accepted. This is it. Thanks for watching, guys.